Hello everyone, in this video we'll find the state equation based on coefficient beta and kappa. So let's get started. First of all, we have information about what the coefficients are. We have an expression for beta and an expression for kappa. Beta is the expansion coefficient and kappa is the compressibility coefficient. In order to calculate what is the state equation, we have many ways to do that. For example, we can use any of these equations. We can use the differential of the pressure, the differential of the volume, or the differential of the temperature. All of these expressions can be used. However, always it's a little bit better if we use the expression who results easier. In this particular case, as far as I'm concerned, the easy equation to use is the expression for volume, because we have a relation directly with beta and kappa. So, this will be the equation that we will use for this problem. Once that we choose what is the equation that we will use, we need to replace the coefficients that we have in here. For example, how can we substitute this term with these coefficients? Well, in this case, we know that beta, by definition, it's equal to 1 over v times the partial derivative of v with respect to t. And we can solve for the derivative. It will be gotten that the derivative is equal to v times beta. Same case for the other term. We know that kappa is equal to minus 1 over v times the derivative. But we need to solve for this derivative. And it will gotten this expression. And we can replace those quantities in this equation. We have this equation. We already have just v times beta minus v times kappa. In this equation, we can factorize v, because we have in both terms. If we do that, we'll get that dv is equal to v times beta times dt minus kappa times dp. So now this term that is multiplying could pass to the other side dividing, and we'll get this other expression. So now we can replace the expression that we have for beta and the expression that we have for kappa, and we'll get the next expression. So now we need to do some algebraic operation in order to get a simple expression and integrate that expression. And finally, we'll get the state equation that we are looking for. In this case, we can observe that we have the same denominator in both terms. So we can we can sum this term, and also this denominator that is divided could pass to the other side multiplying, and it will be gotten this term. So now we can observe in the right side that we have similar terms. For example, in here we have v squared and v squared. We can factorize it and pass it to the other side. But also we can factorize v minus b. In here we have power 1, but in here we have in power 2. But it doesn't matter, we can take only one. And the same thing, we can factorize it and pass it to the other side dividing. Exactly as we have in here. So now in the right side we have only these terms, while in this side we have this quotient. So we can separate these terms in two divisions, like this, and simplify terms. For example, this v cubed could be simplified with this v cubed, and this term v minus v could be simplified with this term in the denominator, and finally we'll get this other expression. The right side is exactly the same. So now we can solve for this term. For example, we can pass this term that is subtracting to the other side with positive sign, and the other thing that we can do is pass this positive term to the other sign, subtracting, exactly like this. So now we can divide all this equation by v minus v. If we do that, it will be gotten this other equation. So if we divided this expression by v minus v, that quotient will be equal to 1. In here, we simplify this term with this term. For that reason, we don't have it anymore in here. If we divided this term by v minus v, we get this quotient. And if this term get divided by v minus v, it will be gotten v minus v squared. So now let's go to do this operation. If we do that, we'll get this other term over here. It's just we must keep the common denominator and solve the operations. If you do this state by state, you realize you will get this expression. Anyway, if we observe, we can factorize the expression r. If we do that, we'll obtain this expression. So now, observe that this term over here, it's very similar to a formula for derivatives. That is the quotient rule. For example, if we have the differential of a quotient, we'll get the denominator times the differential of the numerator minus the numerator times the differential of the denominator, and all of that divided by the denominator to the 2. This is exactly the case that we have over here. We can observe that this expression in brackets is equal to this v, and the temperature in this case is equal to this u. So if that is true, we can write this part like this. In here we have this r doesn't change, and the differential of t, that is the role of u, over v minus v, that is the rule of this v that we have over here. If we do this operation, we realize that we obtain this expression that we have in here. For that reason, it's legal. It's perceived in this way. So now we prepare to integrate all these terms. If we will get the integral of dp, this and this expression and this expression. If we solve each integral, we'll get the next expression. The integral of dp is only p minus 2a. 2a is a constant, but if we integrate this expression, we'll get minus 1 over v squared. Sorry, 1/2 times 1 over v squared, and that half could be simplified with these 2 that we have over here, or for that reason we don't have it in here anymore. And if we integrate this other side, r is a constant, there's no problem in that, and we'll get only the expression that we have in the differential, plus the integration constant. So, in this way, we'll get a state equation for this problem using only the coefficients beta and kappa. So, that's it for today's video. Thank you very much for watching, and see you next time. Take care.